Um, Today's lecture, we're going to be talking about authentication, and in particular, cover some ideas that you might have already seen about or heard of, like tokens, hashing, headers, things that have come up in the spec. And the reason this lecture should be of interest to many of you is because it's kind of like the last piece in the puzzle, really, for iteration 3. And that will probably bring you some peace and probably answer a few questions that you might have been asking yourself so far. So today's lecture is really all about basic security and highlighting how it's an important step when it comes to building good software. This is not a security course, but it is certainly something we think is worth spending an hour on during the course, right? About 36 hours of lectures or whatever. An hour on just to really focus on basic security principles so you can actually, apply them. It's really the tip of the iceberg in terms of a much deeper set of theory that many of you should be interested in going forward. And in particular, we're going to be talking about two key ideas, which is authentication and authorization, and the kind of difference between those two things. So we use Auth as a shortened description for these two words, authentication and authorization. And authentication, which is probably a slightly more relevant part of today, is defined as the process of verifying the identity of a user. This is something that you should all be pretty familiar with because it's what entering, a username and a password is. It's what happens when you lose your student card and you turn up to the Nucleus hub and you say, hey, can I have a new student card? And they say, can you show us some ID or something? It's all the process of making sure that you're like, I am this thing, and you have to prove that you are the thing. And then someone says, great, you've proved it, you are authenticated. Authorization, on the other hand, is the process of determining an authenticated user's access privileges. So essentially, once I know that you're you, what are you allowed to do? And these two definitions can kind of be hard to decouple in some senses. You could kind of argue, for instance, that if you're on campus and you tap into a computer lab or a room with your student card, you might have already been authenticated in the sense that you have the student card, potentially. You could kind of argue that that's not the case. But every time you tap, there's an authorization process to determine if you are authorized to access that particular room. And they're just two pretty basic definitions. We're not actually going to go too much more into the theory of things today, beyond exploring a bit more with tokens and hashing. But UNSW does have more cybersecurity courses on these topics. There's about half or dozen. There's about a half a dozen or so. They're all level 6 courses. You can go look them up in the handbook or the timetable. Should be pretty straightforward. Another example I have here, while we expand on authentication and authorization, is that authentication is checking if you have a username password for a valid Microsoft Teams account, obviously, whereas authorization might be checking if you're an admin or not. Can you add or remove particular channels or groups within something? The definitions kind of write themselves to an extent. Most of what we're going to talk about, though, is authentication, which is this process of, again, verifying, a user is who they really say they are. And let's look at what is the most basic approach to authentication. And it's probably the approach that you've taken in the course so far, which is that step 1, the user registers to, say, your app, right? After they register, you store their username and their password in your data store, and most groups would have done that. And then later on, when the user logs in, you look at the password and username they give you, and you compare it to the data you have in the data store. And if it matches, you're like, they entered the right details, and you authenticate them because, in theory, only they could have entered the right username and password, right? So because they were the ones who, in theory, could only enter it, you're like, okay, it must be you. That's a good basic approach, and it probably looks something a little bit like this. Your code is probably maybe somewhat similar. You've got like some kind of users object within your data store. Here, you got a function called register, takes in an email and a password. you know, if someone tries to register, the return values here are just kind of placeholders, but you get the idea. You store their details against their email. When they log in, you check if what they entered matches everything, and if it does, you know, return true. So pretty straightforward logic. But there's a problem with that. Does anyone know? Anyone in the live lecture here have an idea? It's a pretty obvious one. If you've thought about it for a while. If you haven't, it might not be totally obvious. Do a quick wait for a good answer. Yeah, so Bill says you're storing it in plain text. And Adrian said the same thing. So in the Comp 1531 project, this isn't really a huge problem because you're storing data in a variable which is kind of in memory, which is much less bad than other ways you can store it. But what I want you to kind of extrapolate in your mind is that in a normal production system, that password stored in the in iteration 2, you implemented persistence. So I don't know what I'm talking about. You know this because like it being stored in a variable in iteration 1 style is not too bad, but the problem really comes when you do something like in iteration 2 where you start storing passwords in a file, right? Like you've got a JSON file there somewhere on your computer or on the production computer where it's just someone's password. Like you've opened probably database.json or datastore.json or data.json or whatever you want to call it, and you've probably seen passwords there, right? And it's a little confronting, right? Because you're like, oh my god, that's a password. And if we were to do this in a real software application, the problem is we then have a very risky file because this file just kind of exists on the computer, and anyone at any time, if they were to gain access to it, they could get people's passwords. Thankfully, this is not how nearly every serious service these days, probably basically everyone, wouldn't do it this way. They wouldn't store passwords in what we call plain text, which is where the password is just sitting there in text waiting for a hacker to see. So what we need to try and do is we need to try and hide the passwords. Now this is particularly tricky, right? Because you kind of might know this. Let's say I'm sure all of you have something important. Maybe it's a journal, maybe it's a photo book. I don't know. You probably have something that you value that you don't want people to find. The problem is that when you go and hide the thing that you don't want people to find, it becomes a little bit hard to do something with if you have to go and look for it every hour, you know? So we need to kind of use computers to our advantage here and figure out a way how to hide people's passwords while still being able to check if the password they gave us is correct, you know, because that's the problem. You can't, like you could say, oh, well, you just won't store passwords, but obviously that won't work because if you don't store passwords and someone says, here's my password, how do you know they entered, you know, the right password? So you kind of need to know it. So it gets a little bit tricky. And where this takes us to is a topic on hiding information. And there's two important words that come up in the realm of security here, which is encryption and hashing. Both of these terms are verbs. Well, they're not verbs. Encrypting is a verb and or hashing is a verb. I should call it encrypting and hashing, I guess. But encrypting and hashing are both processes of taking plain text, just passwords, anything, just ASCII characters, and it's the process of taking it and concealing it by turning it into a seemingly random string of characters. And it does this by passing it through, let me just double check what's on the next slide. Yeah, passing it through some kind of cryptographic hash function. It's basically, think of a hash function like a, you know, like a jarbly function. It kind of takes something and spits out seeming garbage. It's a very kind of cool idea. So you kind of put in Fox and you get this giant string of ASCII characters. You can put in something else and you get this other giant string. If I just jump ahead for a second, you look at, like, there's little websites where you can use a little hash function. So I can enter something like hello and it will print at the bottom here. That's like the output of it. So that's like the equivalent here of, you know, we have the blue input and the pink output. There's our blue input. There's the, you know, every single different combination of string will lead to some kind of output here. And it's a very long, scary, confusing output like that. But we mentioned that encrypting and hashing are both ways of concealing information by turning it into a seemingly random string of characters. But encryption is reversible and hashing is irreversible. What that means is that with encryption, encryption is the idea that you can take something that's sensitive and raw, and you can pass it through something that will go and hide it, make it seem seemingly random. Someone couldn't look at this information here and say, oh, I know they're trying to say hello, how are you? But encryption allows you to unreverse it, and hashing doesn't. Now, unreversing it makes a lot of sense. You know, like you think about applications where maybe files. If you ever use a service and they say, you know, we encrypt your files at rest, is something you'll hear a lot. What that means is that they might have stored your information somewhere, but that information is actually encrypted. It's all kind of randomized and garbled on a server, stored on a file system, so that if hackers were to come in and just steal all the files, they would just get gibberish, you know, like this. But they can unencrypt that, because obviously, like, you need, like, if you put your files somewhere, you need a way to kind of access them again, right? Like, it just makes sense. Hashing is irreversible. And you might think, what in the world is that useful for? You know, what is the point of having a way to take useful input, turn it into something seemingly random, and then not undo it? Well, the reason for this is that reversibility does actually make the hiding process finitely less secure. Basically, if you have a way to unhide information, even if you're the only one using that and you're the only one with access to it, that's still like a point of failure. That's still scary because, you know, there's a key somewhere. You know, like as long as there's a key to your house, someone could break in if they compromise you. You know, if someone jumps you on the street. So reversibility is something that we should only really care about if we need it, because reversibility is a capability that will add some risk. So there are times when that convenience is not as critical, which is where we just use hashing, this one-way form of encryption. And hashing is actually perfect for passwords, and we'll show you why. So first thing is, we need to get a sense of how hashing might work, just generally, in a simple file. So let's say, for instance, let me hide all of this for a second. I've got this file here, 9.1 hash, and there's a few things going on in this file. First thing is that we are including this library called crypto. Crypto means cryptography, not cryptocurrency. It's essentially like security, encryption-y stuff. This library lets us do a few fun and interesting things. In particular, it lets us hash things. And what I've got here is I've got a function called getHashOf. And what I do is I give this function some plain text. I give this function some blue. And this function will give me back some pink. Right? So I give the function some blue. I give it back pink. And yellow is the function itself, right? The diagram kind of makes sense. If you pay attention to how this function works, the crypto library here, there's a function called createHash. And this is all kind of a bit confusing, but essentially it's saying use this particular way of hashing, because there's lots of different ways you can encrypt stuff. Use this particular way of hashing. Here's the text I want you to hash. Now go and create some garbage or random stuff with it. And then down here I'm saying, okay, here's my raw input text, my blue text. It's called Big Mac secret sauce. The hash of that is the get hash of that Big Mac secret sauce. So here we have the raw thing, and here we have the hash thing, and then I'm going to console log the hash and see what it gives us. So it's hard-coded, as you can see here, but you'll see if I go npm run ts node on source /9.1 hash, you'll see we get this nice little hash result out of it. That's kind of cute, and you'll see if I come in here and I change this and I change it to Big Mac secret sauce 2 and I run it again, we'll get a different hash. It doesn't look like a slightly similar hash, it looks like a wildly different hash here. See? Like totally different numbers. Now, this is very handy, because if I just look at this information, it doesn't really tell me about much, does it? You know? But the real question is like, okay, cool. Thanks, Hayden. You showed me a way how to take something that makes a lot of sense, like a string, and convert it into something that makes no sense, like one of these hashes, how does that actually help with our authentication issue? And the short answer here, and half of you would have figured this out, where we're going with this is that when someone enters a password, we don't want to store their password in our server. We want to store the hash of their password in our server. Not the password itself, just the hash. So when you have like your kind of typical server like this, right, where you have, this is the same code we had before with your someone registers, you store their email and you store their password. What we're going to do instead, and I've highlighted the exact lines here, is that we're actually going to import our hashing function. You don't have to create a separate file for this. We've just done it for simplicity. Because remember, we wrote that get hash of function here. That'll take in a string, right? String being blue, and it'll give us pink. That's that function, get hash of. So let's say we import that. Now what we're going to do is, instead of storing the password itself, we store the hash of the password. And then the most interesting thing is that, and I think Anthony's said it here, and I'll just quote Anthony. Anthony said, so when they enter the password again, the program is comparing the hashed version to the stored password. Yeah. So what that means, and you can kind of visually demonstrate it here, is like at the point of registration here, right? Someone gives us their password, and what we do is we hash that to hashed password, and then what we do is we only store the hash password. Now, while again immediately like you intuitively think, well, if I can't reverse the encryption because the hash is one way, like you can, yeah, let me get back to reversing it soon. But if you can't reverse the encryption, what's the use of the hash password? Because I don't know what someone's password is. Well, you don't really need to, because when someone comes over here and logs in 10 minutes later, they enter a password. But what you do after they enter a password is you also hash that. So you hash their input, and in theory, if they've given you the right password, these two things should be the same. Right? And just as a practical example here, let me show you. I'm going to close your eyes. I mean, you don't have to close your eyes, but let's pretend that my password is llama. Now the hash of llama is this giant thing here. So let's imagine that my data store somewhere now looks like this. You know, emails hayden.smith@unsw, and my password is the hash like that. I don't know what the real password was, but now what happens is, let's imagine someone's trying to log in, and if they're trying to log in, let's say they're trying a bunch of different passwords like koala. So they enter koala, and what we do is we go, what's the hash for koala? It's that. Does it match what we have? No. So it's not the password. I don't know what Hayden's password actually is, but it's not koala, because if it was koala, if we hashed it, we would get something else. And then he tries Hayden koala 234, and then we compare it here and we say, nope, those hashes look different. And then eventually, say someone guesses it right, or more, hopefully you enter the right password and you enter llama. What happens is this is run, and we look at it and we go 9384F9. Oh wow, okay, it's actually the same thing. So they give us their password as a login. We hash it every time they try and log in. We compare the hashes and we go, oh, sweet. Okay, it must be you. So this is an incredible way to store passwords, essentially. It's a very simple way, not like a more industrial way is a bit more involved. It's an easy way to store passwords without actually storing the sensitive information, because now if there's like a hacker that comes along and they get access to all your data, or say your database.json, all they're going to get is this file here with the hashes. And with the hashes, you can't really do a lot. And, you know, it's like, why can it only go one way? Why is there no function that can reverse this? That's quite a deep topic. You're probably going to have to get into like the world of finite mathematics and stuff. There's some other courses you can do at uni, or you can go deeper into cybersecurity and computer science. But essentially, the short story is that it's very challenging to undo it. It's very challenging to get something like this and to turn it back into the plain text itself. you can I just don't want to waste airtime on it because it's not relevant, but you can go and Google it and watch some videos and they'll talk about, Jacob's asked about bit operations. They'll talk about prime numbers and multiplying two large primes together and the difficulty of factorizing two large primes. It's a really interesting topic, but essentially, it can be very easy to take a string. Like, imagine for a second. Now, I can't even explain it trivially because I'd be like, well, let's imagine you take every character and you turn it into its ASCII number and you multiply it by 9. And like that might work, right? Like if we thought of, probably won't work. Like you look at this, okay, what are the ASCII characters of these? I'm just going to guess them because I don't remember ASCII off the top of my head. Let's go like 62 and then 96 and then like 90, like 88 and then like 97 and then like 88. And then you multiply all of those by 3 for no particular reason. And then after you multiply them all by 3, you add them all together. Oops. And after you add them all together, you get a new number, and that new number might be like something like that. And this is like your hash result. Except you could represent that in a string form if you really wanted to, right? And it'd be very hard if someone came along, like, let's just try and represent each of these as a character, where 4's like D, F, E, E, F. It's very hard to take something like that and be like, where did this come from? Now, if you're smart about it, you'll be like, well, I know how it was generated, so kind of just unwind it. And the short answer is that, again, without going into the finite maths of it, there are certain things that are just not that easy to undo. Go read up on it. It's not what we're here today about. Point is, hash function like this, really easy to go one way, very difficult to go the other way. Now, I say it's really difficult to go the other way. I wouldn't feel like I am doing you all justice if I don't take a moment to talk about that. And this has nothing to do with the course here. This is more just for your own general knowledge. Whilst it is very difficult to undo, I can come here and I can say, there's the hash for A. And I can go write that down. A is that. And then I can enter B. And I can copy that and say B is that. And I can enter C. And I can do the same thing. And what I'm doing here as I do this is I'm creating something that they'll refer to as a rainbow table. It's essentially a table of all the different hashes. And this is really helpful because let's say that you hack into, the Comp1531 major project database and you get a bunch of hashes like this. Now all you have to do is grab this hash and enter it into your big file you've created of all the different password permutations like AA, AB, AC. You know what I mean? You can kind of write them all out. And again, this is just for general knowledge. Obviously, what this implies to you and something you should think about a lot is that simple passwords, even if your password is protected, it's not really protected because for simple words like cactus, someone's probably already, if I look up SHA-256 rainbow table, you'll see this. Cactus has this particular hash. But if I come, I hope they have a SHA-256 one. Yeah, they do. If I come here, you'll notice that as I enter that, it'll tell me that it's cactus. And that's because someone's already gotten a computer that go through every single ASCII combination and figure out the hash so that when you get a hash, you can figure out what the string is. So that's why long passwords are really important, because let's say you pick a long password, like cactus makes me cry. This is a really long string, and you'll see if we try and crack that one, it hasn't been found yet. No one's generated that yet. You might be thinking, well, that's strange. Why has no one done it? Surely it's a big planet with a lot of computers. And this is where we fall back into the interesting world of kind of maths, right? Where let's imagine, a password. Let's just say a password can be any of 70 characters. So if you have a one-letter password, let's say with 70 characters, there's only 70 different ways the password can be. 70 different letters. If it's a two-letter password, then it's 70 to the power of 2 different ways it can be. And then again, let's imagine for a second that to calculate one hash, to just simply run this program that I wrote here, with a different thing like A or AA, let's imagine that it takes, let's be quite conservative and say, let's imagine that it takes 0.001 seconds to run that function. Well, now this one is going to take, you know, this 70, let me pull this up beside it. This, you know, so like this, and I know I know there's a handful of you that know a lot of this stuff already because you're really interested in it. But I'm just trying to prove a point to people who haven't thought much about it. It's like, you have a 1-character password, obviously that's going to take you 70 times 0.001 seconds, right? Which is 0.0 seconds to get every single 1-character password. And then you look at your 2-character passwords, which are 70 to the power of 2. You know, and that's going to take 4.9 seconds. Then we'll do like, say, 4 characters, 6 characters. We'll do like 8 characters, 10 characters. We'll do 12 characters and we'll do 14 characters. We'll just do like a bunch of really interesting ones, right? So, just trying to guess I'm really dragging this example out a bit. Yeah, 70 to the power of that equals something. Yep. Could just use Excel for this. I think last time I used Excel because I probably had a bigger brain back then. But let's have a look at this. So if you have a 4-digit password and it takes 0.01 seconds, well, that's going to take, you know, that many seconds, which is that many minutes, which is 6 hours, say. Okay, now it definitely doesn't take that long. 0.001 seconds is probably a really long time. But let's say this one takes, you know, 6.7 hours. Okay, well now we do it with 70 to the power of 6. That's how many hours that takes. Well, 24 hours in a day, 365 days in a year. So now, you know, a 6-character password, to figure out the hashes of every single 6-character password, you're now looking at 3.7 years, right? And when you do 8, now you're looking at that many years. So, you know, and the whole story of this, it's not really anything exciting. It's really just the effect of exponential math, right? Because when you get to 10, you start to get into, you know, like 89 million years. And suddenly at 12, you know, you get into huge numbers, right? Like longer than the universe has been around, I think. You get the point. Encryption, cryptography. If this interests you, go learn more about it. A lot of it's propped up on this idea that there's things to do in one direction that you can't do quickly back, but you can kind of hack around it by like storing a big database of all the different hashes. But there are so many different combinations of things that you just it's physically not possible to go and store them all at all, you know? Like one thing I always think about is they estimate that there are approximately 10 to the 80 atoms in the universe. And let's say you divide that by like 70 to the 16. That's still really big. That's okay. Let's say 22. No, it's got to be super big, obviously. Let's try like 35. Still too big. Oh, sorry. What am I doing? Speak out loud. All I'm really doing here is saying that if you were to have a 43 character password where you could have 70 different digits, there are more combinations of passwords that you could have than there are atoms in the universe, as far as our best estimates go, you know? So it really does get to a point, and this is why they talk about long passwords being important. It gets to a point where someone's just not going to guess it. If it's long enough, it's just not going to be guessed. No one's going to figure out what it is. Obviously, that's maybe not the case. Like, don't sit here being like, if I have a 10-character password, I'm really safe. Because a lot of people have 12-character... A lot of people have 16 character passwords that are just going to be password. And obviously, you know, if you're smart and you're making this like special table of things, you're going to probably put that in at some point or something. Anyway, I'm about to now just kind of talk a little bit about tokens and iteration 3. Now that we've kind of covered the basic theory of it. And I wanted to see if there are any questions before we moved on, because this lecture's nearly done after we talk about iteration 3. Matthew says, is it open source? Yeah, most kind of encryption libraries are open source. Yeah, I don't know of many that aren't. I mean, if this makes sense, encryption isn't really about computers, it's about math. You know, and these libraries are just expression of that math, and I don't, as far as I know, you can't patent a lot of, I don't know, maybe you can patent math, I have no idea. Anyway, let's have a quick tangent to iteration iteration 3. So if we come down in iteration 3 to the section on tokens, cool. There's two things to iteration 3. The first thing is that you need to store passwords in an encrypted form. That's super easy because we've already shown you how to do that. We showed you right here. It's in the lecture slides, right? Passwords should not exist in your data store anymore. The second thing, which is a bit more interesting though, which is kind of alluded to here, is about, it's what you would call session hijacking, and I'm aware that this piece of text might confuse some people here because it's a new thing we've added to the spec. So, you know, there's definitely ways we could improve our explanations of it. But basically, most of you have implemented sessions in iteration 2. And what that means is that if you look at your data store, you might have something like this, users, where, you know, it might be like email is Hayden at UNSW, password is soon going to be like some hash, and then you might say sessions, and then you might have a list of session IDs like this, right? Maybe you have something similar where people, you know, every time they log in, they get a session, and when they log out, that session's removed or something like this. One of the problems with this approach is that people can basically, it's really hard to get into the depths of it because there's a bit more kind of web knowledge here, but maybe we should look through the sample flow here. A sample flow of a user logging in is that they call auth login. The server generates a token and the hash of the token and a secret, and then the server returns the hash as the token value and the response's body. Okay. So what you might have done in, say, iteration 2 is when you have your like auth login function, say, takes in an email and a password, this function might, you know, do the checks, and, you know, if they're all good, you're like, okay, they're logged in. And what you might return is you might return an object that says token, and that token might just be, say, you know, a session ID of some sort. You know, like users, you know, 2.sessions0 or something like this. You're returning the session ID. But one thing that we are asking you to do for iteration 3 is to be cognizant that sometimes it's possible for people to hijack sessions. And what we mean by this is that, let's say that we have 2 users, and maybe I'll just change this data store here a little bit. So let's say we have 2 users, and the second user here is, you know, Jake at unsw.com, and Jake's got a different password. And let's say I'm a hacker, and what you actually respond to me with, and I'm going to use just hard-coded here, like stub code, is you return to me a token. This is the token, and that token is just like a session ID which might be like 1, 2, 3, because I'm Hayden. And this is all good and this is all cute, but the problem is if I'm a hacker and I've gotten that from your login function, what I could start doing in my subsequent functions is tampering with the token. And what I mean by that is, let's say that, I'm a hacker and auth login returned me a simple token that looks like this, 1, 2, 3. I might come along when I call subsequent functions and say, you know what, I'm going to change this to a bunch of random numbers. Like this. But the problem with, and this is bad because eventually, I might guess the right number if I was to change it randomly. One day I keep changing it and eventually I change it to that. 8997879. And then the server says, oh, hi Jake, I can see it's you because you've entered the right session number. And you might think, well, we could make the session number longer, we could randomize it. Yeah, and that's like kind of helpful sometimes. But what can be even better here is if what we do, and this is a little bit heady, I think this is definitely one of the parts of the course that might confuse people, is when you return a token, what you do is you try and return not just the session ID, but a session hash. Now, you can do this a few different ways. Some people might have already done it another way. There's just a method to achieve a goal, which is to make your tokens tamper-proof. And I want to keep coming back to that. Everything we're talking about is about trying to make the tokens tamper-proof. And to make it tamper-proof, I'm not just going to return 1, 2, 3, but I'm actually going to return a hash as well, which is going to be the combination of, say, the session ID, 1, 2, 3, as well as what we call a secret string. So I'm just using my hashing file here. And this secret string can be anything you could hard code it in, which might be, like lemon tree or something like this. And maybe I can pull this out further and say, constar, session equals 1, 2, 3. So the message is just the session plus the secret. So what happens is now when your function is actually going and returning the token in the login and register function, it's not just returning a session ID, but it's returning a session ID and a session hash like this. Why this is so important and why something like this is so useful, and it's very interesting to think about, and it's the foundation of, in reality, libraries do this kind of stuff for you, is that if someone gets this token and they start tampering with it, they start changing this to 8997879, they won't be able to get past you, because one of the first things that you can do when you get a token like this is you can take the session ID, you can go and pump it into, say, this SHA thing here, 1, 2, 3, and it's a slightly different one. Oh yeah, sorry. You pump in 1, 2, 3 plus lemon tree like this. This website here is doing something slightly different to how we were doing it. Anyway, let me just put this let me put this hash in here. So, it's not working. That's okay. Bugger. So let's say someone comes along and they change this from 1, 2, 3 to 8997879. They don't know how to change the session hash to the right thing. So when you look at their token on the server in your, channels view, your channel details and your messages and all this kind of stuff, when you try and generate the hash for that, now suddenly you get a different hash. So you on the server can then look at the hash you got from that, and you can look at the hash they gave you, and this is clearly wrong, right? This is the wrong hash. It doesn't match. It doesn't match the 8997879. And it's like, well, what if they hash it themselves is the next question, right? What if they come and take their 8997879 and every time they pick a random session ID, they also hash it? Well, the problem is they can't, because they don't know this particular secret which lives on your server. You never expose that to them. Obviously, yes, by having this little secret, in theory, it's another piece of sensitive information that if someone hacked you, maybe they could figure it out. maybe they could go and grab it from the source code or something, but that's not really a concern because we're talking about sessions here. And if someone has your source code, you've got some problems anyway, and a few other details. But the point is that this is a way to secure your payloads to make them tamper-proof, because now someone can't just go and change the information in the token because they don't know how to get the new session hash. This is sometimes what you might call a signature, where I don't just return the information that I'm interested in, which is the payload here, but I also return a signature, which is it's basically like only the server can produce the right signature for that payload. So if someone tampers with the payload, they can't generate the new right signature or the new session hash. So that's kind of a way of doing it. It's probably the way I'd encourage you to do it. Sometimes, like the other way that we talk about in the spec is that instead of sending session IDs, you can actually just, the token can just be the session hash, and then all you do now is you just like store the hash instead in your data structure up here. So your sessions are just hashes. That's really not too different from generating a big session ID though. That's kind of like the equivalent of just generating a big random number. So I'd probably more so recommend that you try and do what I've suggested, which means you don't actually need to store more information in the data store, right? Because you're just actually only returning that information as the return value. Because all this secret hash then becomes is like really all it is just, hash of 1, 2, 3 plus the secret. That's all that is. And when you have your function that checks if the token's right, it's just doing the same thing. It's just hashing the session ID in the token and seeing if it matches the other thing in the token. Before I kind of keep moving and finish off this last example with the tokens to do with the headers, again, I want a quick pause and ask if people have questions, because this is quite a heady topic and I want to make sure we nail it. So I'll do a quick pause for 20 seconds and see if people have questions about this. Anthony says plus. It's very interesting stuff. Derpy says, so is it just making a hash of the ID with the secret? Yes. Yes, that's it. And then just returning that as part of the token. I want to be clear because this language is so easy to mess up, but it's like, this is the token. This is not the token. Often people just kind of use the word token everywhere, and I think even in the spec, even in the spec it's written a bit poorly. Not that it matters. This is just a pet hate of mine, so I'll make sure that's cleaned up. But token is what you get back from the server. Token is the whole object, right? A token is actually, well, it depends what you define it as. I'm not going to go too crazy about that because you can interpret it different ways. Yeah, so Anthony says, yes, it all makes sense. So to recap, there's 3 things here. There's hide your passwords with hashing. There's use hashing to add more to your token to make your token payloads tamper-proof. And then number 3 here is putting your token in the header. And I'm just going to quickly touch on this because it is mentioned in the spec. But basically, if we go back to some servers from an earlier iteration, how the old spec looked was that if you made a post request for most of your requests, you would often pass the token through the body. So at the top of most of your functions might be something like this, request.body.token, say, and then you might have a function that's like, if this is what you might have done previously, if is not valid token then, return error. Maybe you had something like this. But the point is, in all these cases, you would get that token from the query or the body. For this iteration, we're asking that instead of that, we actually get it from the header. So instead of getting it from the body like that, we actually want you to get it from the header, like this. Now, how does that change what you do? Well, when you're writing your tests, it's going to change it because now you're going to send the token not through the query string, but you're going to send it through the header like this, You're going to send your token here, or whatever it is. And same for this request here. You'll do something like this. And the question is kind of like, why do we do that? Why do we have to send it through this headers thing? Headers is like the metadata associated with the request. It's kind of like, when you send an envelope, the headers are like, the address and stuff on the front. It's kind of like, it's like not the main body of it. It's just the metadata. And then also, just I guess to complete this, if you're trying to send it through, say, the ARC client or something like that. How do I get to apps again? I always forget how to open up apps. How do I having a moment? How do I open up apps in Chrome? Someone help. Launch. Okay. Silly. So it's really quite simple because previously when you made a GET request, you'd put some data in the URL, but there's just a header section. You know that because of the content type header. And same with POST requests, there's headers, body, and variables. The reason we do this is actually really, really simple. If you go and have a look at HTTP requests, you have GET, POST, PUT, and DELETE. Then you can send data through the query and the body and headers. Right, so queries just like through the URL, bodies like, what the body is, and the headers is something separate. You can send data through the query with any request. You can only send data through the query with POST and PUT. That's why POST and PUT, you send it through the body, GET and DELETE, you send it through the query. But with headers, you can send it through everything. But here's the important thing. This is unencrypted, whereas these two are encrypted on modern web, right? So what that means is that the header is the only place where for every request you can send encrypted information. That's why we send the token there, because the token is generally considered to be sensitive, because whilst we said before, if we go back to what we were talking about, we said that we had covered a few things today, like 1 and 2. This here, like this whole hashing thing, it just makes your token tamper-proof, but that doesn't stop someone stealing your token. Because if someone can steal your token, it's like they've authenticated as you, and they don't need to log in. They can just use your token. Right? Like if I stole your token, I could just start calling server functions with that token, and they'd think I'm you, because that's all you need, right? Like when you're checking if someone's something, if you're checking if someone is someone, all you're checking is against the token. So that's why we move it to the header for iteration 3, not in the body or the query, because in iteration 2 you would have been sending the token through the query sometimes and the body other times. Right? And if you're not sure what I mean by like the information is unencrypted with the query, think about this. Every time you bookmark a page, you bookmark the entire URL. So you think about a website like this, right? When I bookmark this page, I bookmark bing.com SHA-256 rainbow table. So if you just go and put your token up in that URL, it's all kind of public on the internet. The Australian government can see it. Your ISP can see it. There's no encryption there. The URLs you access aren't encrypted. This is that whole thing again about government surveillance and stuff. Is like, and you should be like aware of this. Is that when you send, well, I don't know what the NSA is up to, but when you send messages on like Facebook Messenger, all that information you're sending is encrypted. So in theory, neither Facebook or the government can see what messages you're sending, right? In theory, because it's all encrypted, because it's all being sent through a body, typically. And therefore, anyone who tries to kind of intercept the data on the way across the internet, they just see gibberish because it's all encrypted. And we've just talked about encrypted today and how we make things look seemingly random. But every URL you send access is not encrypted. So every time you access any page or anytime the URL changes, I'm pretty sure nearly all of that data is being stored by ISPs and all the government these days. So, that's just something to keep in mind. And that's also why we don't send sensitive data through the query, because it's not considered safe. Anyway, just to wrap this one up, I hope that was interesting. I hope that was insightful and helpful, frankly. If it wasn't, I'm sorry. Let's tackle it on the forum or ask a question in the next 30 seconds. But the last thing, we talked mostly about authentication today. There's nothing really to cover with authorization, because authorization is just a check, and you'll deal with this in your project pretty simply, because you'll have someone call a function like edit channel or add user, and you will authenticate them by looking at the token, or you'll look at the token, which is their authentication, and once you see that it's Hayden, the next step is you see, is Hayden an admin or is Hayden not an admin? That's really you seeing what Hayden is authorized to do. So there's nothing really to talk about on that topic in this lecture. We were more just exploring definitions. If you could please leave some feedback, that would be great. We're going to go take a 5-minute break, and then we're going to keep going into the next lectures. So let's just assume that we'll keep going at say 7:10. That's probably easiest. So yeah, cool. Anyway, thank you. Leave some feedback.